Okay, so guide 1, 2, part C. The first thing we're going to discuss is polynomials and what polynomials are, and then some terminology involving polynomials. So you've been working with polynomials pretty much all through high school, right? A polynomial an example would be something like this. Okay, so that's an example of polynomial. It's all in terms of one variable. We usually use x for polynomial, not all the time. All the exponents on the polynomial is positive whole numbers in this example, right? Okay. So in general, and then we're going to talk about some definitions when we determine the polynomial in general. So all polynomials, usually we write them in standard form. Standard form means from the highest exponent all the way down to the lowest exponent on the variable of the x. Okay. The coefficient in front of the x with the highest exponent, that's called the leading coefficient, and I'm going to call that a to the subscript n. Okay? All the coefficients are going to call a, but then I need to differentiate between the different a's, so I'm going to put a little n underneath. Okay? And then x to the exponent. So then the next coefficient, right, is the next one in order. So I'm going to call that n minus 1. And the same thing with the exponent on the x. And I'm just going to keep going all the way down until I get to a subscript 1, x to the exponent 1, and then a subscript 0. So this is just this in general. Okay, so this will cover any single polynomial. Doesn't matter if the highest exponent is 10 and then the next one could be 9. Every single exponent doesn't need to be represented. It can go from, like this guy here, 4, 3, and then skip the 2 and then down to 1. Okay, it doesn't matter. They don't have to all be represented. So this term here is called the leading coefficient. And coefficient, recall, it's just a fancy word for saying the number in front of the variable. The last term, which is a subscript 0, that's just going to be a number, and that's called the constant term. So not all polynomials have a constant term, because not all of them will necessarily just have a number at the end of it. Okay? The highest exponent in the polynomial expression, which is usually written first, we write it in standard form, so this exponent right here, that tells us the degree of the polynomial. So for example, in my previous example, the degree of this polynomial is 4, so that's the highest exponent. The leading coefficient is -6, and the constant term is 3. So I'll just color code them for the benefit of the note. So what you need to be able to do is identify these terms from different polynomials. Okay? So any questions on that? It's pretty straightforward stuff, right? Okay. So just try a quick example. Given f of x, x okay, so just stop talking there. So given that the polynomial f of x is equal to 6x squared minus 10x plus 8x to the power 4 minus 6, the first thing we want to be able to do is to express it in standard form. So determine polynomial in standard form. So in standard form, all you have to do is rearrange the terms so that the x's go from descending order from their exponents. Okay, so this 8 and 6x squared and the minus 10x and the minus. So that's standard. Any questions on that? Okay. Question B, what's the degree of this polynomial? You would say the degree is 4. Okay, so again, I want you to get used to knowing notation. So if I ask for the leading coefficient, I might write out on a test, determine the leading coefficient. Or I might say that. Okay, determine a to the subscript n. And I want you to know that a to the subscript n and the leading coefficient mean the same thing. Okay? So the leading coefficient is 6. And then the same thing with the constant term. I might say determine the constant term. Or I might say tell me what this is. A to the subscript 0. And that's just the one that doesn't have an x with it, a variable. And in this case, it would be negative 6. Any questions on that? Jacob? Yes, it would be. Okay. Now, any questions on that? Thanks, Jacob. And I'll do that, obviously, right? That's why pencils have erasers. People make mistakes, right? Correct me. Don't just sit there and say, oh my God, I did something wrong. Should I say something? Tell me for sure, okay? Because this is going into D2L, and if you're watching it later, you're like, where did that? Thanks, Jacob. Okay, and so any questions on that terminology? Okay. So the next thing we're going to talk about is the factored form of a polynomial. This is standard form. Okay? Factored form. As soon as you see the word factored, you should think brackets, right? So the factored form of a polynomial would be something like y is equal to negative 8 bracket x minus 3 x plus 1. So that's a polynomial in factored form. In general, and if I haven't said so already in my notes, remember that f of x and of y are interchangeable. They mean the same thing. It just means the function value, right? So in general, f of x is equal to, there's always going to be a number out in front in factored form. If there's not a number, that number's 1. There's always has to be something there. So I'm going to write down k for that number. There's always going to be a 1. And then x minus a, x minus b. And you can keep going on forever depending on the size of the polynomial. Okay. But the most important thing is to be able to use the factored form to determine the zeros of a polynomial. Okay. So determine the zeros. We'll start off with an easy one. And I'm going to give it to you in standard form, then we're going to go put it into factored form, and then we'll determine the zeros. So if I say I have a simple polynomial function, something like this, again, everybody in this class should recognize that as being a quadratic, and you should say, okay, quadratics are U-shaped curves, so I know what that looks like. It's a parabola, right? I want to put this into factored form, because from factored form, then I can determine the zeros. So to put it in factored form, it's a simple trinomial. I look for two numbers that multiply to give 10 and add to give 7, which would be 2 and 5. So I factor it. Now I'm asked to find the zeros. What are the zeros of this polynomial function? Okay. How did you get that? Awesome. Okay. This is what I'm going to get on a test all the time, and I'm going to take marks off, so I'm going to show you what I want you to do. Okay? Because this asks you to find the zeros. It's pretty easy. Like, you can look at this right away, and you'd say, okay, the zeros are x is equal to negative 2, and x is equal to negative 5, which is exactly what Scratch said. That's it, perfect. Okay? What didn't I write here anywhere? Yeah? You don't even need to do that. You can skip from this line to this line, but you have to do something. What was I trying to say? You have to. You have to put a 0 there, okay? Because if not, it's f of x. You have to solve for 0. You have to set the equation equal to 0. Okay? You can skip that middle step here where you write that. That's okay. I don't mind that. But you can't solve for 0 unless you have the equation equal to 0. Okay? And you will lose a half mark for bad form. Okay? So if ever you see on your test BF, that means bad form. That means you've done something incorrect mathematically. Just like in English, right? You just can't take words, write them all over the page, and expect the teacher to read them in the proper order in which you wrote them all over the page. Right? It has to be a process. Okay. So when the polynomial is in factored form, it's pretty easy, hopefully, to identify the zeros. Right? So when we are given an equation in factored form, and I ask to find the zeros, essentially what you're doing is you're taking each factor of the polynomial and setting each one of them equal to 0. Right? Again, you don't have to show this step. I'm going to show it for the benefit of the note. Okay, so I'm setting this equal to 0. I do want you to write equal to 0 somewhere. Now, if you don't want to show the next step where you're setting each one of them equal to 0, how many factors do I have here? Three. Exactly, right? 1, 2, 3. Because I have 3 different x's, right? So actually, if I was to ask the degree of this polynomial, what would it be, do you think? How many x's are there? 3. So when you multiply these all together, you're going to get x to the power 3. So it's going to be the degree 3 polynomial. Make sense? Okay. So that's why sometimes it's beneficial to have it in standard form. Say you're looking for the degree, it's a lot easier to read it off. But here, you have no idea what the zeros are. If it's given to you in factored form, then it's easier to read off the zeros, right? Okay, so then from here, you'd set each factor equal to 0. And then solve. So x is equal to 0, x is equal to 5 over 2, and x is equal to negative. Whenever you are doing anything involving fractions, leave them as a fraction unless it's a terminating decimal. So if you wanted to change this to 2.5, that's okay. Do not change this to negative 1.333333. You can't express it in exact value. Okay, so you would leave it exactly like this. And we'll talk about when to round off and when to do estimated values throughout the course as well. Make sense? Okay. Another common kind of mistake people will make is when they get a question like this. And I see this all the time, so I'm going to write down what I see, and then you guys tell me what I did wrong. So I'll get that, I'll say on a test, determine the zeros of this, and I get this all the time. And you can do this if you want, right away, write it equal to 0. That makes sense. Why doesn't it? There? Right, negative 4 equals 0. Do I have to worry about this negative 4? Why not? Why did I have to worry about the negative 3 here, but not there, right? Exactly. There's no x besides, just a constant. You don't even include that, right? Because again, as Jacob said, negative 4 isn't 0, so you can't say they're equal to each other. So then you would just write down. Perfect. Are we all good with determining the zeros from factor form? Pretty straightforward, right? So what we're going to be doing, not in this unit, but in the next 3-4 unit, is we are going to be given expressions like this that you can't factor by grouping. It's impossible to factor by grouping. We're going to learn how to factor them so that we can put them into factored form to find the zeros. And that's what the whole 3-4 guide is going to be all about. Okay? The next thing we're going to talk about, and you've done before, is intervals of increasing and decreasing. So remember that in mathematics, just like in reading a novel, you always read from left to right, same thing in mathematics. When you're describing a graph, you always go from the left to the right. Okay? So a function is increasing when it goes up to the right. A function is decreasing when it goes down to the right. They never talk about what's happening in terms to the left. Okay, so if I give a quick example of a function. Y, X. I'll do my function in blue. There's my function. I'm going to say this point right here, put it at -2. I'll say that's close enough to 0. And this one here, this one stop. And this one here, let's say it's -4. This one here, we'll say is kind of halfway in the middle, so I'll say 5 over 2. Actually, yeah, let's see. So the x and the y axes are just number lines, right? So as we go to the right here, we're going to positive numbers. And as we increase, okay, we go on forever. What are we heading towards? If I just keep going forever and ever? Infinity. Does anybody know the symbol for infinity? Okay. Exactly. Okay. So as I head out here, I'm heading out towards positive infinity. As I head out this way, I'm heading towards negative infinity. As I head up forever, I'm heading towards positive infinity. As I head downwards, I'm heading towards negative infinity. Make sense? Okay. So what we're going to talk about here is the increasing and decreasing intervals. So increasing intervals, decreasing. Okay, so the function is increasing when it goes up to the right. So my function from here, it's coming down. This arrow means that's going up this way forever. So it's coming down, it's decreasing all the way to here. Then it starts to increase, and then it starts to decrease again. So if I kind of color code it, this is where my function is increasing. This is where my function is decreasing. And it starts to decrease again here. Where a function changes from increasing to decreasing, right here, at that point, that's called a turning point. When a function changes from decreasing to increasing, it's still called a turning point. But then, as we go through the course, we're going to learn that they actually have different names. So they're both turning points, but this one's the top of a hill, so we call it a maximum, and this one's the bottom of a valley, we call it a minimum. We'll get into that a little bit more as we go through. Okay, so when you're asked for intervals, you're always asked for the x value. So what x values, between what x values is my function increasing? What would you say? Look at that. Good. So between -2 and between 5 over 2, between that interval right there, the function's increasing. Does that make sense? Okay. So x is less than 5 over 2 and greater than -2. When you're reading inequalities, always read the variable first. So if I was reading this, I would say, okay, x is greater than -2, x is less than 5 over 2. Okay. If you prefer to write it like this, that is totally fine. I write my intervals in a different way. When I say I write it, it's not like I made it up, it's mathematically sound, right? So what I do is I write it in interval notation. So interval notation looks like this. My starting point is -2. I go up to 5/2, and then I have to put indicate whether the -2 is included or not. Because if I wanted to include the -2 here, what would I do? In an interval, how do I include the -2? Anybody remember? So if I wanted to include it, I want it to be equal to -2. I'd write a little equal sign underneath. So this now says x is greater than or equal to -2, right? So sometimes the end value is included, sometimes it isn't, right? In notation, if it's included, you put a square bracket. If you don't, if it's not included, you put a round bracket. So I'm going to write that down here. Square bracket, oops. Square bracket, numbers included. Round bracket, not included. So what's the only thing that could be confusing between my notation? What does that look like? Bracket, -2, comma, 5/2, bracket. Okay? Yeah, it looks like a point on the graph. Okay, so you have to understand in the context of the question you're dealing with an interval. So you never have to decide which one it is. It's always going to be one or the other. Okay, so the decreasing intervals. So the function is decreasing on the left side of -2. So I want it to be less than -2. The function is decreasing on the right side of 5/2. So x is greater than 5/2. So x is less than -2, x is greater than 5/2. Okay. When you're including the intervals of increasing or decreasing, right, these turning points need to be included some, so you just can't forget about them. Okay. Doesn't matter which one it goes with, actually. You can put the equal sign with this guy or with this guy, but it can only be with one of them. So I'm going to put it with that. You have to include the -2. You can't just ignore it. And the way I would write this is my starting point here. I'll do this one first. 5/2 is my starting point. I want to include it, so I put a square bracket, and it's going to head all the way up to, not a number, positive infinity. And you can never put a square bracket around positive infinity because you can't achieve it. So then this one here, it would go all the way from here, which is negative infinity, up to -2. You want to include 2, but not negative infinity. So the ones in red here is the interval notation. This and this mean the exact same thing. This means the exact same thing. Do whichever one you feel comfortable with. So just a couple of examples, just to kind of get the interval notation going. So if I had a number line, I had -3 to 4. So I want you to show that all three of these things mean the exact same thing. It's just three different ways of expressing it, and you can do whichever one you feel comfortable. Okay? So say I had the number line look like this. So this means all the numbers between -3 and 4. 4 is included because it's colored in. -3 isn't included because it's not colored in. Okay? So with my inequality notation, I would say x is between 4 and -3. X has to be less than 4, but it has to include 4. So I'd write x is less than or equal to 4. X has to be greater than 3, but not include it. So I'd write that. So that and that mean the exact same thing. And then the way that I would write it is -3 to 4 is my interval. -3 is not included. 4 is included. So if I ask you an interval of increasing or decreasing, and the interval was from -3 to 4, you can write the answer in any one of these ways, as long as you communicate one of them. Make sense? As the course progresses, if you get used to this notation, it's going to be a lot easier. Any questions? Okay. Next example. Determine f of x in, not is, in standard form. I'm just going to give you a picture of a function, and I want you to come up with the equation of that function from the graph. So I'm going to draw. It's not going to be to scale. I'm just going to put the best I can. Kind of whack there. Okay, so in order to determine the equation of a function, you're going to need some information. You're going to need the zeros of the function. So I'm going to say my zeros are -3, 1, and 5. And also you're going to need a point on the function, which I'm going to give you the point 3 and -48. So when I say I gave you the zeros of the polynomial function, the zeros refer to what on the graph? So if I said -3, 1, and 5, what are they on the graph? Correct? Right, so what do we call those? Nope. We call them zeros, but they're called another thing. Yep. The other x-intercepts. So remember the x-intercepts on the graph mean the zeros of the function. Okay, I just wanted to remind you of that. The x-intercepts on the graph mean the zeros of the function. Okay, so how can I determine the equation of f of x in standard form from this information? Yep. So what are they? You're giving me the zeros, right? Okay. So x equal to -3 is a 0, x equal to 1 is 0, x equal to 5 is 0. Okay, so that's a good starting point. How does that help? If I go back to the examples, because ultimately what I want to do is the reverse of this question, right? Here it was in standard form. Then we put it in factored form, and then I was able to determine the zeros. I'm just kind of going backwards. So if the zeros are that, what must it have been in factored form? Anybody at the back of it? Yeah. That makes sense? So that's what it must have been in factored form. F of x is equal to that. What am I missing? Yep. Pardon? Like expand it all out and collect it? Okay, so I still don't have it in standard form, right? So I'm going to graph that function, which was bracket x plus 3 times bracket x times 1 times x. Okay, so there's my function. And the x-intercepts of that we know are -3, 1 and 5, right? Okay. How about if I graph this one? What do you notice? Functions stayed exactly the same? No, change. What stayed exactly the same? Right? Yeah, 0, right? So there's going to be a number in front there. Even if I change this to this, like -9, it's going to change the function. You see it changing, but the zeros are staying the same. There's an infinite number of functions that have those zeros. I have to find a particular one for our example. So going back to the note earlier, remember that I said every single time a polynomial is in factored form, what's it going to have in front of it? Looking in this area. Okay. Not necessarily 0, but the k value. There's going to be a number that's going to make this a particular polynomial that's going to have these zeros and pass through this point. So I need to put in that k value. If you don't, and take this as a hint, this is the most common thing people do wrong on the question on the test. They forget that k value. Okay? How do I determine what this actual k value is? So a lot of times in math, they give you information, right? In a question. If you haven't used all the information in a question, sometimes you should try to use it. What information have they given us that I haven't even used yet? Okay? Right, the point at the bottom. This point, a point on the function means if I plug 3 into the function, what should I get as f of x? What should my answer be? Really? Yeah, -48. So I'm going to do that. And then plugging 3 in. So you notice the only value that you are left with that you don't know is k. But this gives you a nice equation to solve for k. So -48 is equal to k times 6 times 2 times -2. 6 times 2 times -2 is -24 times k. Divide both sides by -24, and k is equal to 2. So now you determine the exact value of k that's going to give you the zeros of -3, 1, and 5, and you're going to ensure that it passes through this point. Okay, so now you're going to do what Surprise said, where you have to multiply everything out with left-like terms. So here's your k value is 2. So if you get a question like this on your test, and you will, and you're able to skip some steps, feel free to do that. If you're not, take your time and write down each one of those steps. Okay? So I'm going to take 2 and I'm going to distribute it inside the bracket. Does this 2 go into this bracket, and this bracket? Brandon's saying yes. This top one's saying no. You know why? Yeah, it only goes in the first one, right? It would be like taking 2 times 3 times 4 times 5. You wouldn't take 2 times it by 3, then times it by 4 times it by 5, right? Okay? And again, I said that because that's a really common mistake people are going to make. So if I multiply it into the first bracket, I get that. And I'll multiply these 2 guys together. And I get that. So now it's just a matter of taking 2x, multiplying it by each term there. So I'll get 2x cubed minus 12x squared plus 10x, and then now distributing the 6 in, plus 6x squared minus 36x plus 30. Okay, so now just collect your like terms. So the x squareds, the x's, and then so that's the polynomial, the function standard form. So again, some things to notice, right? The degree of this polynomial is 3, right? You could tell that because that's the highest exponent in the standard form. You could also tell that because in the factored form, there's 1, 2, 3x, right? Say if I wanted to ask the leading coefficient of this polynomial, you would say it is, yeah, maybe 2. How would you get it from the factored form? If I said, what's the leading coefficient of this guy, how would you do it? Right? And then multiply to each one of the front terms to figure out what that front term would be. How do you think you'd do the constant term now? Because it's pretty easy to see that positive 30 is the constant term. How would you get 30 from this? Yeah, exactly. So this times that is 6, times that is negative 6, times that is 30. That's what you get. Okay? So you can get all those answers I was asking before in factored form. It just takes a little bit of work. So factored form is much easier for you to find the zeros. Okay? Standard form is much easier for you to identify the leading coefficient, the degree, and the constant. But you can do both of each. Any questions of what we've done today? Okay, so just like before, I'm going to save this.